Hey, Dr. Clark here, and in this preview video, we're going to be looking at section 4.3, homogeneous linear differential equations. Let's take a look. So first, remember the difference between a homogeneous and a non-homogeneous linear differential equation. For non-homogeneous, you have this g of x term. For homogeneous, that g of x would be 0. And for a linear differential equation, we can have these coefficient functions a n of x down to a1 of x and a0 of x. It would be simpler if we set all those to be constant. So what we're going to look at today is a homogeneous linear differential equation with constant coefficients, which would look like this. And as you can see, that's a lot simpler than the full general linear differential equation like so. And we're going to learn that we can solve this thing over the next little bit. And to get us started, let's take the simplest case, first order. So ay prime plus by equals 0. Now, we've solved this problem before using the method of integrating factors, or it's also separable. You can do it either way. And we know that the answer is in e to the kx. And the question is, what is the k? Well, let's say we do it as a separable differential equation. We end up with e to the negative b over ax by, separating, integrating, exponentiating, and such. And so k is negative b over a. But what I also want you to do is to kind of think of this like a linear function, like mx plus b kind of a thing, or ak plus b. And if you just solved that for k, you would also get negative b over 2a. Okay, so there's some connection between the look of this and the answer, e to the negative b over a x, and just looking at this and solving for k. Now, maybe that's a coincidence and maybe it's not. Let's see why it's not a coincidence. So if we just guessed the solution was e to the kx, then we could put in e to the kx for y and y prime. We'd have k e to the kx because of the differentiation. And then you would solve this, you would end up with this equation. So if y was e to the kx and y prime was k e to the kx, and set equal to 0, e to the kx is never equal to 0. So we can actually divide both sides by that. That reduces to ak plus b. Set that equal to 0, you get k equals negative b over a. So there's this natural way where assuming the answer is going to be an e to the kx, and then later on figuring out what the k is, actually works. And the question we will have is, can this be extended? So what if you had a second derivative? Second order problem, like a double y double prime plus by prime plus cy equals 0. Can you do this same trick where assuming the function is e to the kx, and then later on figure out what the k is? Well, I don't know. Is e to the kx even the answer to this question? So we'll find out. But that's the idea. We're going to take this notion of guessing a solution of a particular form and then later on figuring out which version of that function it is. And it turns out to work pretty well for the linear case. And we're going to find out later that it's actually going to work just as fine for this second order problem as well. Okay, so so in class, when we get into class, what we're going to do is learn to solve these homogeneous, linear, constant coefficient differential equations. So we're chipping away, working our way up, solving more and more complicated problems, but these are some of the simpler ones, and we're going to be able to solve these. So we'll see you in class, and we'll get it done then.